Let's elaborate more on functional dependence and functional independence using the Jacobian. Let's see how it is very useful in determining the relationship between functions and variables over there. Suppose you see this example. Suppose we have n functions, say f1, f2, f3, and each function in turn depends upon n variables. Say in this example, uh, let's take, we may want to know whether there exists some relationship between these functions. For example, f1, which is a function of x, y, z, like x plus y by z, f2, which is also a function of x, y, z, like y plus z by x, and f3 is a function of x, y, z, y times x plus y plus z by x, z. Now we have f1, f2, f3, which are functions of x, y, z. Then we would like to check whether in some way f1, f2, f3 are related, right? I mean, if they are related, then some relationship exists. Then we say that f1, f2, f3 are dependent. If you want, you can check f1 into f2 is f3 is equal to f3 plus 1. But however, in real life, the situation may not be as simple as it is in this example. Therefore, we need to find some criteria which would ensure the existence of some relationship between the given functions. There comes a Jacobian. We'll see that Jacobian provides us a necessary and sufficient condition for the existence of some relationship between the given functions. But before making precise as to what we mean by relationship, we look at the following question and answer it satisfactorily. In calculus, we have seen that a real valued function depends in a certain domain, uh, and if its derivative is zero at all points on the interval, then f is a constant function. This is analogous to a function of several variables. See, if the derivative vanishes, that is a function of a single variable. We want an analogous analogy for the same for a function of several variables. We see that those functions, all of whose partial derivative vanish throughout some domain, are constant. But here, the word domain has a different meaning. It's not just a set on which the function is defined. Then let's see what is a domain. Let's see a couple of examples. So, moral of the entire discussion is, if the Jacobian vanishes, then they are functionally dependent, else they are functionally independent. For example, you take some function f of xy equal to d power x sine y, and g of xy is x plus log sine y. What's the domain? X belongs to R and y belongs to 0 to pi. And since y belongs to 0 to y, I think it is a strip bounded by the lines y equal to 0 and y equal to pi. And let's see what is the Jacobian. J of fg by xy equal to e power x sine y e power x cos y, 1 cos y, that is e power x cos y, cot y rather, e power x cos y minus e power x cos y, that's equal to 0. And it's equal to 0 for all xy in our domain. What's our domain? That's a strip between 0 to pi. Y equal to 0 to y equal to pi. In other words, g is simply the function log f and a function of a function. And we'll see that f of small f and g equal to 0, even though dou f by dou u is not equal to 0 and dou f by dou v not equal to 0. Okay, so they are functionally dependent. F and g are, we can express f in terms of g. Another example, u equal to x cube minus y cube into z cube, v equal to x square plus y square z square plus xyz. And w equal to x minus yz are functionally dependent, and also find the relationship between them. If u, v, w are functionally dependent, we know that the Jacobian vanishes. J of u, v, w by j of x, y, z equal to 0. Now, what is j of u, v, w by x, y, z? Ux, uy, uz, and vx, vy, and vz, wx, wy, and wz. What is dou u by dou x? 3x square. What is dou u by dou y? Minus 3y square z cube. And what is dou u by dou z? Minus 3y cube z square. Similarly, what is dou v by dou x? 2x plus yz. And dou v by dou y is 2yz square plus xz. And dou v by dou z equal to 2y square z plus xy. Similarly, what is dou w by dou x? 1. And dou w by dou y equal to minus z. And dou w by dou z equal to minus y. Now use determinant algebra and take out the common terms and simplify, right? Then we see that virtually two columns are identical here. So the determinant vanishes. So they are functionally dependent. Now we need to speak u in terms of v, and we need to have a relationship between u, v, w. We see that x cube minus y cube z cube equal to x minus yz into x square plus xyz plus yz square. That is indirectly u equal to vw is the relationship between these three variables. Let's take another example. Let u equal to 3x plus 2y minus z, v equal to x minus 2y plus z, and w equal to x times x plus 2y minus z. What is the Jacobian of u, v, w? Now we want to know whether u, v, w are related or not. Or that's functionally dependent or not. Now let's check the Jacobian. J of u, v, w by x, y, z equal to ux, uy, uz, vx, vy, vz, wx, wy, w. What is ux dou u by dou x equal to 3, and dou u by dou y equal to 2, dou u by dou z equal to minus 1. Similarly, dou v by dou x equal to 1, dou v by dou y equal to minus 2, and dou v by dou z equal to 1. Dou w by dou x equal to 2, and dou w by dou y equal to 2, dou w by dou z equal to minus 1. And you expand the determinant, we see that it's equal to 0. So they are functionally dependent. Now we need to have that relationship between them. The relationship between them is u square minus v square equal to 8w. Okay. This example we have seen already. Right. Take another example. U equal to x cos y, v equal to x sin y. Domain is a set of all points xy where x is greater than 0. Now we want to know whether they are functionally dependent, u and v. So j of uv by xy equal to ux uy and vx vy. That is equal to cos y minus x sin y and sin y into x cos y. That is x cos square y plus x sin square y. That is equal to x. And we see that x is greater than 0. So the Jacobian is not equal to 0 because x is positive throughout our domain of discussion. So they are functionally independent, right? Okay, we'll stop here.